Good morning everyone. Today we are going to discuss on the course Advanced Operation Research for second MSc Mathematics. We are going to start with the module 1 branch and bound technique. First of all, let's start with the introduction of OR. Operation research, often shortly called as OR, is a discipline that deals with the development and application of analytical methods to improve decision making. It is considered to be a subfield of mathematical sciences. OR is an analytical method of problem solving and decision making that is useful in the management of organization. In OR, problems are broken down into basic components and then solved in defined steps by mathematical analysis. Now let's see the process of operation research. This can be broadly broken down into following steps. The first step is to identify a problem that needs to be solved, constructing a model around the problem that resembles the real world and variables. Next, we use any one model to derive solutions to the problem. Then test each solution on the model and analyze its success, implementing the solution to the actual problem. Let's discuss the characteristics of operation research. There are three primary characteristics of all operation research efforts: optimization, simulation, probability, and statistics. When it comes to optimization, the purpose of operation research is to achieve the best performance under the given circumstances. Optimization also involves comparing and narrowing down potential options. Simulation, this involves building models or applications in order to try out and test solutions before applying them. Regarding probability and statistics, it includes using mathematical algorithms and data to uncover helpful insights and risks, make reliable prediction, and test possible solutions. So now let's discuss the first module, integer linear programming. Branch and bounds comes under this. So what is integer linear programming? Integer linear programming, commonly called as ILP, it's a type of optimization problem where the variables are integer values and the objective function or equations are linear. Next we can discuss what is a mixed integer linear programming, generally called as MILP problem. It has continuous and integer variables. Mixed integer linear programming, MILP, is often used for system analysis and optimization, as it presents a flexible and powerful method for solving large complex problems, such as the case with industrial symbiosis and process integration. Let's start with the branch and bound technique. There are a lot of techniques to solve integer linear programming. The first one is branch and bound approach. The branch and bound approach is based on the principle that the total set of feasible solutions can be partitioned into smaller subsets of solutions. That is, the problems is broken down into small subsets and then it's solved. These smaller subsets can then be evaluated systematically until the best solution is found. Now let's discuss the algorithm of branch and bound method. In step 1, solve the given problem as an ordinary LPP. First of all, you have to convert it as an ordinary linear programming problem. Then in step 2, we have to examine the optimal solution. Terminate the iterations of the optimal solution to the LPP, satisfies the integer constraints. Otherwise, you can go to step 3. So what is step 3? Now divide the problem into two parts. In problem 1, xk less than or equal to t. In problem 2, xk is greater than or equal to t plus 1. While solving problem 1, the objective function is to maximize z equal to cx, subject to the constraints ax less than or equal to b, xk less than or equal to t, or kx greater than or equal to 0. While solving problem 2, xk is greater than or equal to t plus 1. Our objective function is to maximize z equal to cx, subject to ax less than or equal to b. Xk is greater than or equal to t plus 1, where x is greater than or equal to 0, where t is the largest integer. In step 4, now solve problem 1 and 2 separately. Step 5, if for any other subproblems, optimal integer solution is obtained, then that problem is not further branched. Otherwise, you have to move to the next step. The branch and bound method is not a solution technique specifically limited to integer programming problems. It is a solution approach that can be applied to a number of different types of problems. The branch and bound approach is based on the principle that the total set of feasible solutions can be partitioned into smaller subset of solutions. These smaller subsets can then be evaluated systematically until the best solution is found. When the branch and bound approach is applied to an integer programming problem, it is used in conjunction with the normal non-integer solution approach. We will demonstrate the branch and bound method using the following example. So now let's take a real-time example. The owner of a machine shop is planning to expand by purchasing some new machines, presses and lathes. The owner has estimated that each press purchased will increase profit by $100 per day and each lathe will increase profit by $150 daily. The number of machines the owner can purchase is limited by the cost of the machines and the available floor space in the shop. The machine purchases, prices and space requirements are as follows. It is given in a table form. So, the machine which he is going to purchase is a press and lathe. The floor space in square feet is given as 15 for press and 30 for lathe. Purchase price is $8,000 for press and $4,000 for lathe. The owner has a budget of total $40,000 for purchasing machines and 200 square feet of available floor space. The owner wants to know how many of each type of machine to purchase to maximize the daily increase in profit. The linear programming model for an integer programming problem is formulated in exactly the same way as a linear programming. Examples and characteristics 2 or 4 of the text. The only difference is that in this problem, the decision variables are restricted to integer values because the owner cannot purchase a fraction or portion of a machine. The linear programming model is as follows. Now the linear programming model is as follows. Maximize Z equal to $100 x1 plus 150 x2. Now recall, x1 is to purchase press and x2 is to purchase lathe. Subject to the constraints, 8,000 x1 plus 4,000 x2 less than or equal to $40,000 and 15 x1 plus 30 x2 is less than or equal to 200 feet square. The first equation is regarding cost and the second equation is regarding the square feet available, where x1, x2 are greater than or equal to 0 and integer. x1 equal to number of presses and x2 equal to number of lathes. The decision variable in this model are restricted to whole machines. The fact that both decision variables x1 and x2 can assume any integer value greater than or equal to 0 is what gives the model its designation as a total integer model. We begin the branch and bound method by first solving the problem as a regular linear programming model without integer restriction. That is, the integer restrictions are relaxed. The linear programming model for the problem and the optimal relaxed solution is maximize Z equal to $100 x1 plus 150 x2 subject to 8,000 x1 plus 4,000 x2 less than or equal to $40,000, 15 x1 plus 30 x2 less than or equal to 200 square feet, x1 x2 greater than or equal to 0. Now the solution is x1 equal to 2.22 and x2 equal to 5.56. Substituting x1 and x2 in the objective function, we get Z equal to 1055.56. These solutions are obtained either by graphical method or using any computer softwares like Lingo or any or related softwares. The branch and bound method employs a diagram consisting of nodes and branches as a framework for the solution process. The first node of the branch and bound diagram, shown in next figure, contains the relaxed linear programming solution shown earlier and the rounded down solution. Now the upper bound is equal to 1055.56, where x1 equal to 2.22 and x2 equal to 5.56. Now note down x1, x2 and z are not integers, and lower bound equal to 950, where x1 equal to 2 and x2 equal to 5. If we take the lower bound where x1 equal to 2 and x2 equal to 5, we get z equal to 950. Notice that this node has two designated bounds, an upper bound UB of $1055.56 and lower bound LB of $950. The lower bound is the z value of the rounded down solution, x1 equal to 2 and x2 equal to 5. The upper bound is the z value for the relaxed solution, x1 equal to 2.22 and x2 equal to 5.56. The optimal integer solution will be between these two bounds. Rounding down might result in a suboptimal solution. In other words, we are hoping that a z value greater than $950 might be possible. We are not concerned that a value lower than $950 might be available. Thus, $950 represents a lower bound for our solution. Alternatively, since z equal to $1055.56 reflects an optimal solution point on the solution space boundary, a greater z value cannot possibly be attained. Hence, z equal to 1055.56 is the upper bound of our solution. Now that the possible feasible solutions have been narrowed to values between the upper and lower bounds, we must test the solutions within these bounds to determine the best one. The first step in the branch and bound method is to create two solutions, subsets from the present relaxed solution. This is accomplished by observing the relaxed solution value for each variable, x1 equal to 2.22 and x2 equal to 5.56, and seeing which one is the farthest from the rounded down integer value, that is, which variable has the greatest fractional part. The 0.56 portion of 5.56 is the greatest fractional part, thus x2 will be the variable that will branch on. Because x2 must be an integer value in the optimal solution, the following constraints can be developed: x2 less than or equal to 5 and x2 greater than or equal to 6. In other words, x2 can be 0, 1, 2, 3, 4, 5 or 6, 7, 8. It can take any one of the value, but it cannot be a value between 5 and 6, such as 5.56. These two new constraints represents the two solution subsets for our solution approach. Each of these constraints will be added to our linear programming model, which will then resolve normally to determine a relaxed solution. This sequence of events is shown on the branch and bound diagram in the next figure. The solution at nodes 2 and 3 will be relaxed solutions obtained by solving our example model with the appropriate constraint added. Now let's show it in a figure. Upper bound equal to 1055.56, x1 equal to 2.22. This is the initial value we got. x2 equal to 5.56. Lower bound is 950. x1 equal to 2 and x2 equal to 5. Now these are the nodes. In first node the value got is 1055.56. It is branched into nodes 2 and 3. Let's see what will happen in 2 and 3. First, the solution at node 2 is found by solving the following model with the constraint x2 less than or equal to 5 added. Maximize z equal to $100 x1 plus 150 x2 and subject to the constraint. Here the new constraint is x2 less than or equal to 5 and x1 x2 greater than or equal to 0. Remaining two constraints remains the same. The optimal solution for this model with integer restriction relaxed is x1 equal to 2.5, x2 equal to 5 and z equal to 1000. Now we can see the solution has optimized to x1 equal to 2.5 and x2 is fixed to 5. Now the new z value is 1000. Next, the solution at node 3 is found by solving the model with x2 greater than or equal to 6 added. Now maximize z is the same objective function subject to the first two constraints remains the same, where x2 is greater than or equal to 6, x1 x2 greater than or equal to 0. The optimal solution for this model with integer restriction relaxed is x1 equal to 1.33 and x2 equal to 6 and z equal to 1033.33. These solutions with x2 less than or equal to 5 and x2 greater than or equal to 6 reflect the partitioning of the original relaxed model into two subsets formed by the addition of the two constraints. The resulting solution sets are shown in the next graph as figure. So we can solve this as a graphical method. Solving we get x1 equal to 2.5 and x2 equal to 5 and the maximized value is $1000. In the next figure we get x1 equal to 1.33 and x2 equal to 6 and the maximized z value is $1033. Notice that in the node 2 graph in figure, the solution point x1 equal to 2.5, x2 equal to 5 results in the maximum z value of $1000, which is the upper bound for this node. Next, notice that in the node 3 graph, the solution point x1 equal to 1.33 and x2 equal to 6 results in the maximum z value of $1033. Thus, $1033 is the upper bound for node 3. The lower bound at each of these nodes is the maximum integer solution. Since neither of these relaxed solution is totally integer, the lower bound remains $950. The integer solution value already obtained at node 1 for the rounded down integer solution. The diagram in figure reflects the addition of the upper and lower bound at each node. So, upper bound equal to 1055.56, x1 equal to 2.22, x2 equal to 5.56, lower bound equal to 950, x1 equal to 2 and x2 equal to 5. You can see this in this figure. In node 2, the maximum value, the objective function, the maximum value is 1000. In node 3, the objective function maximum value is equal to 1033. Since we do not have an optimal and feasible integer solution, yet we must continue to branch the model from either node 2 or 3. A look at previous figure reveals that if we branch from node 2, the maximum value that can possibly be achieved is $1000. However, if we branch from node 3, a higher maximum value of $1033 is possible. Thus, we will branch from node 3. In general, always branch from the node with the maximum upper bound. Now, the steps for branching previously followed at node 1 are repeated in node 3. First, the variable that has a value with the greatest fractional part is selected. Because x2 has an integer value x1 with a fractional part of 0.33 is the only variable we can select. Thus, two new constants are developed from x1. So, x1 less than or equal to 1, x2 greater than or equal to 2. Now, from the branch, the node 3 is branched into two parts, x1 greater than less than or equal to 1 and x2 greater than or equal to 2. Now, the new nodes 4 and 5 are got from the branches. Next, the relaxed linear programming model with the new constraints added must be solved at nodes 4 and 5. However, do not forget that the model is not the original, but the original with the constraints previously added, x2 is greater than or equal to 6. Consider the node 4 model first. Maximize z equal to 100x1 plus 150x2. Now the nodes are x2 greater than or equal to 6 and x1 less than or equal to 1, x1, x2 greater than or equal to 0. First two remains the same. The optimal solution for this model with integer restricted relaxed is either we can get by graphical method or using computer software. X1 equal to 1 and x2 equal to 6.17 and z equal to 1025. Next, consider the node 5 model. Maximize z equal to 100x1 plus 150x2. The new nodes are x2 greater than or equal to 6 and x1 greater than or equal to 2. The other constants remains the same. However, there is no feasible solution for this model. Therefore, no solution exists at node 5 and we have only to evaluate the solution at node 4. The branch and bound diagram reflecting these results is shown in the next figure. So, in cumulative we get branching the third node, we get in the node 4 the value of z is 1025.50 when x1 is less than or equal to 1, and when x1 greater than or equal to 2 we get an infeasible solution. So thereby the node 5 ends. The branch and bound diagram in previous figure indicates that we still have not reached an optimal integer solution. Thus we must repeat the branching steps followed earlier. Since the solution does not exist at node 5, there is no comparison between the upper bounds at node 4 and 5. Comparing nodes 2 and 4, we must branch from node 4 because it has the greatest upper bound. Next, since x1 has an integer value, x2 with a fractional part of 0.17 is selected by default. The two new constraints developed from x2 are x2 less than or equal to 6 and x2 greater than or equal to 7. This creates the new branch and bound diagram in next figure. The last linear programming model with the new constraints added must be solved at node 6 and 7. Consider the node 6 model first. So UB equal to 1055.56, x1 equal to 2.22, x2 equal to 5.56, which you have started in the beginning. Node 1. Node 1 branches to 2 and 3. 3 branch to 4 and 5, where 5 is an infeasible solution. Now the node 4 branched into 2, 6 and 7. So x2 equal to x2 less than or equal to 6 and x2 greater than or equal to 7. These are the two nodes. Maximum is z equal to 100x1 plus 150x2, subject to 8000x1 plus 4000x2 less than or equal to 40,000, 15x1 plus 30x2 less than or equal to 2000. New branches are x2 greater than or equal to 6, x1 less than or equal to 1, x2 greater than or equal to 6, x1 and x2 greater than or equal to 0. The optimal solution for this relaxed linear programming model is x1 equal to 1, x2 equal to 6 and z equal to 1000. Next, consider the node 7 model. Maximize z equal to 100x1 plus 150x2 subject to 8000x1 plus 4000x2 less than or equal to 40,000, 15x1 plus 30x2 less than or equal to 200, x2 greater than or equal to 6, x1 less than or equal to 7. The new constraint is x2 greater than or equal to 7, x1, x2 greater than or equal to 0. However, the solution to this model is infeasible and no solution exists at node 7. The branch and bound diagram reflecting these results is shown in the next figure. This version of branch and bound diagram indicates that the optimal integer solution x1 equal to 1, x2 equal to 6 has been reached at node 6. The value of 1000 at node 6 is the maximum or upper bound, the integer value that can be obtained. It is also the recomputed lower bound because it is the maximum integer solution achieved to this point. Thus, it is not possible to achieve any higher value by further branching from node 6. A comparison of the node 6 solution is as follows. So, node 1 branches into 2 and 3, node 3 branches into 4 and 5, 5 is infeasible, node 2 is, in node 2 we got integer solution, again 4 is branched into 2, where upper bound is 1000, x1 equal to 1 and x2 equal to 6, lower bound is 1000, x1 equal to 1 and x2 equal to 6. Now the solution is 1000 at node 6 and in node 7 we get an infeasible solution. Those at nodes 2, 5 and 7 shows that a better solution is not possible since we get an infeasible solution. The upper bound at node 2 is 1000, which is the same as that obtained at node 6. Thus node 2 can result in no improvement because in node 2 we got z equal to 1000, in node 6 also we got z equal to 1000. The solution at nodes 5 and 7 are infeasible and thus further branching will result in only infeasible solution, so that further branching is not required in node 5 and 7. By the process of elimination, the integer solution at node 6 is optimal. Since node 6 cannot be branched further, we can stop at node 6. In 7 we got infeasible solution. In general, the optimal integer solution is reached when a feasible integer solution is generated at a node and the upper bound at that node is greater than or equal to the upper bound at any other ending node, that is the node at the end of the branch. In the context of the original example, this solution indicates that if the machine shop owner purchases 1 press and 6 lathes, a daily increase in profit will be $1,000 is as a result, because x1 equal to 1 and x2 equal to 6. Since x1 represents press, he can purchase 1 press and 6 lathes, which will result in a profit of $1,000 per day. In the context of the original example, this solution indicates that if the machine shop owner purchases 1 press and 6 lathes, a daily increase in profit of $1,000 will result. The step of the branch and bound method for determining an optimal integer solution for a maximization model with less than or equal to constraints can be summarized as follows. First step, find the optimal solution to the linear programming model with the integer restriction relaxed. At node 1, let the relaxed solution be the upper bound and the rounded down integer solution be the lower bound. Step 3, select the variable with the greatest fractional path for branching. Create 2 new constraints for these variables reflecting the partition integer values. The result will be the new less than or equal to constraint and a new greater than or equal to constraint. In step 4, create 2 new nodes, one of the less than or equal to constraint and one of the greater than or equal to constraint. In step 5, solve the relaxed linear programming model with the new constraint added at each of these nodes. In step 6, the relaxed solution is a upper bound at each node and the existing maximum integer solution at any node is the lower bound. If the process produces a feasible integer solution with the greatest upper bound value of any ending node, the optimal integer solution has been reached. If a feasible integer solution does not emerge, branch from the node with the greatest upper bound. Now return to step 3 if it is not branch. For a minimization model, relaxed solutions are rounded up and upper and lower bounds are reversed. So thank you. We have summarized the branch and bound method at the end. We can meet in the next module. Thank you.